Welcome to this ninth lecture video for Physics 4A. For the last few weeks, we covered force analysis problem-solving strategy that we call standard strategy and kinematics, in particular projectile motion. So, in this set of lecture videos, we will finish one version of the banked turn problem that we saw in the last lecture video, and then we will work on some exam type questions, in which you are asked several related questions about a single physical setup. The 2D kinematics question will have you work through an aspect of 1D kinematics, followed by an analysis of projectile motion. The question shown here comes from the portable TA, by the way. Pulley-and-masses question uses our dynamics lab setup, with a few additional questions that I think you answered in lab. Finally, the pull with friction question is the kind of question where a level of mathematical maturity becomes useful, as you are asked to reason through some consequences and results using the analytical expression that you derived, rather than plugging in numerical values at the first opportunity. This is the last of the lecture videos specifically covering standard strategy and kinematics. Our next lecture video will look at a computational tool that you have seen me use at least once, and after that, we start our coverage of the conservation laws.
Okay, so if a car takes a banked curve at less than the ideal speed, friction is needed to keep it from sliding toward the inside of the curve. I guess that's right. Yeah, if it's standing still, it would slide kind of in towards the inside of the curve. So it says calculate the ideal speed to take it, and what is the minimum coefficient of friction needed for a frightened driver. So I'll do both parts. Part A will kind of naturally show what the frictionless version looks like, because the ideal speed actually has friction force going to 0. So this is the picture you should have in mind. So this is one of those where to represent the full set of information, you really need two views. You need a top view, which will show you the curvature of the road and kind of how the car is moving. If it looks like I'm basically drawing the same picture that I drew for the train, yeah, it kind of is. But the rear view will now look more interesting because I now have to draw the banked curve. So you are imagining looking at this car from the back. You are maybe standing here and you're looking at the car. Then you will have the cross section of the road, which will give you that banked angle, theta. And this is what the car will be like. It's going into the page. So, all right. And so, yeah. So let me draw a free body diagram. Try to talk about the interactions without there being a free body diagram. So the free body diagram of the car looks like this. There's no force along the direction of movement because it's moving at, I'm assuming it's moving at constant speed. This is V ideal. So the only forces necessary are kind of within this plane of rear view. That's why we draw this rear view at all. So I like to draw gravity first. You always have gravity, mg. And here, what keeping the car from accelerating downward is actually this surface here. And because that is at an angle, theta, normal force has to be in this direction. And and that actually goes with because this car is moving in a circle, it needs to have centripetal acceleration. So the way the forces are arranged here, you can arrange it in such a way that there's no acceleration in the vertical direction, but there's a horizontal acceleration towards the center of the circle. So yeah, so all this seems fine. Let me kind of draw what the components of normal force would be. Here's the x component, or what's going to become x. Here's the horizontal component and the vertical component. Let me just move on to the second step in the standard strategy and draw my coordinate axis. So my coordinate axis will look like this. And this is actually the thing that sometimes tricks a lot of people in dealing with a question like this, is that despite the appearance of the inclined angle or inclined plane, because your acceleration is horizontal, your axis should also be straight, horizontal and vertical. Just be mindful of that there. So let me just track this angle theta through different geometry. So that's the same angle theta here. This angle here is 90 degree minus theta. So what theta should be is actually this angle here. So that gives me this component, the x component, as n sine theta. It's on the opposite side. And this angle is n y is equal to n cosine theta. All right. And that's step number 3, breaking down forces into components. Yeah, and because it's asking about ideal speed, where we kind of want friction force to be 0, that's all the forces there is. I don't need any other forces other than gravity and normal force. The normal force should be enough to allow the car to make that turn. So I'm done through step number 1, 2, 3. Let me finally do step number 4, which is writing down Newton's second law equations. So I'm gonna need to write down 2 equations, one for each dimension, one for x, one for y. Net force in the x direction is going to give me x component of force, and sine theta is equal to mass times acceleration, and I recognize that it's a centripetal acceleration, so it's gonna be v squared over r. And in the y direction, I have net force in the y direction is equal to, I have 2 forces, the y component of normal force and cosine theta minus mg is equal to 0. All right, I have 2 equations. Let me count my unknowns. I don't know normal force. I do know theta. I do know radius. Oh, I don't know v. Oh, yeah, v is what I'm solving for. So I don't know v, and I think that's it. I have 2 unknowns, and I have 2 equations. So once again, I'm taking stock of my unknowns, 2 unknowns, and my information, 2 equations. I think I have everything I need. So let me go through that. So I guess what I'm going to do is I'm going to eliminate normal force, solving this for v. So I'm going to go through the same steps I go through. I'm going to use substitution approach. Once again, you don't have to use substitution. There are other ways you can kind of do this more quickly. But the reason I like a substitution is because it's kind of standard approach you can use for 99% of the questions. So even though it's sometimes a little bit more steps, it's kind of worth knowing the one boring vanilla way of doing everything. So I'm going to solve equation 2 for n. That gets me n is equal to mg divided by cosine theta. And this is going to become my tool, 2 prime, my tool for eliminating n, normal force, from my system of equations. So plugging 2 prime into 1, this is what I'm going to get. 1 and 2 prime gets me mg sine mg over cosine theta times sine theta, that's the left hand side, is equal to m v squared over r. Oh, I didn't even talk about m not being known, but I kind of knew it was going to cancel out. So, all right, I guess I need to solve this for v. Let me solve it for v. So solving it for v, I have v squared is equal to r times g. And this time I can actually write it as sine theta over cosine theta. But let me not do extra work and just write it as tangent theta. And if I take square root, I can get rid of that square sign there. So for this scenario, what the speed should be is a square root of rg tangent theta. I think I have enough to just plug in the numbers. So let me do r 100 times g, 9.8 times tangent theta. And the way I plug it in this calculator is first I enter the angle, 21. And then I type tangent, and I can kind of verify it's doing that correctly. Is equal to, oh, that's the squared value. So I need to take the square root of the whole thing. Okay, so 19.39 or 19.4 is what I need to do. Oh, that question, I think this question we solved it for the rounding issue already. So, so this should be 19.4 meters per second. So that's the easier part of the question. And the reason I wanted to do this question in particular is because it has this part B where you now have to worry about friction. So it says, what is the minimum coefficient of friction needed for a frightened driver to take the same curve at this speed? And let me use Wolfram alpha to 20 kilometers per hour is 5.556 meters per second. So in part B, we have not taken away any of the information that was already present here, but it just now specified V. So what I hope, that should be actually enough information for you that you can't just take what you did for part A and simply plug in V equals that, because then that's not what the value of V is. This is the value of the V. So really in part B, what has been done is it has changed the physical situation altogether. So let me use the diagrams that I've drawn for part A to note where it has changed. So what has changed are the forces. So when I was drawing the diagram for part A, I took this to be the case, that the friction is 0. And everything I've done here is consistent with that. So now we have to consider the possibility that friction isn't 0. So, all right. So if I have non-zero friction, I have to think about what direction it'll be. And the way you figure out the direction of friction is one, you imagine what would happen without friction. So without friction, you have a driver who is not going fast enough. So the driver will tend to kind of sliding inward. The question actually said as much, sliding towards the inside of the curve. So without friction, the car it'll have kind of slide along. So it always had the horizontal component. It'll now have the vertical component of acceleration as well. So after having figured out what would happen without friction, what you do then is you introduce friction in such a way to oppose what's going to happen without friction. So here, so friction can only go in the direction along the surface. So you are choosing between choice 1, down the slope, and choice 2, up the slope. So between those two choices, the choice that will give you the upward component of force to oppose the downward sliding is this direction here. So you'll have a friction force that's pointed that way. that's going to be necessary to keep the car from sliding down. So, we have straight axis, which means this needs to be broken into components. So let's do that. I guess we need to. So let me just zoom in and kind of draw in the things I need to draw. So this is the x component, y component, and this angle here, that same angle. So this is the angle here. So the x component is actually adjacent. So the x component of friction will be f cosine theta, and the y component will be f sine theta. This, by the way, is why you need to always draw the triangle. You can't automatically go with sine and so, in one, cosine is going with y, and in the other, sine is going with y. You just have to draw the triangle, track the angle to the triangle, and do that. So deriving friction force will now modify my equations. So let me go and do that. In the interest of saving time, let me just move these out and then draw in my friction force. So friction force is going in the negative x direction. So I have minus f cosine theta. And it has a vertical component too. So it's gonna be even, so let me erase this. I'm not gonna be able to use this anymore. So the vertical component of friction, let me move this out so that I can. So I guess vertical component will be adding to the normal force. So it'll be plus f sine theta. Yeah, that's all the changes I need to make. And now that I have friction, this f becomes unknown, and we can solve for friction force eliminating normal force. Now, unfortunately, that's not what the question is asking. The question is asking for the minimum coefficient of friction. So I think I'm still going to need to write down an additional equation so that I can actually switch my unknown from normal force to this coefficient. So let me write that down. When you're dealing with the minimum circumstance, what you can say is, all right, so for the minimum level of friction coefficient, I can say that the friction force is equal to U minimum needed times the normal force. Now, when we're dealing with the static friction force, this would have been an inequality, but that's for kind of mu that might be above the minimum. If you're dealing with the minimum, then the equality holds. So let me actually solve this for, what do I want to solve this for? I guess it doesn't matter. This is already solved for friction, so let me use that to eliminate friction from all my equations. So then I'm gonna be, so I guess I'm not switching out normal force. I'm gonna be getting rid of friction, so I'll have two unknowns then. I'll have normal force and the coefficient of friction. And then once I have that, I'm going to get rid of the normal force and finally solve for the coefficient of friction. So let me do that first step first. Let me use equation 3 to get my equations 1 and 2 prime. So let me clear out some space here. So by combining equation 3 with equations 1 and 2, what you're going to get is, so I'm going to get n sine theta minus instead of friction, mu mean n, I'm just going to say mu, n cosine theta is equal to mv squared over r. That's going to be my equation 1 prime. My equation 2 becomes n cosine theta plus, so mu n instead of friction, times sine theta minus mg is equal to 0. And that's going to be my equation 2 prime. So to solve for mu, it looks like the easiest thing to do is, I guess I'm going to solve both equations for n, and then I can just set one equal to the other. It's a kind of substitution, but I can see this is going to get algebraically complicated. So let me just do it this way. So solve for n. Then that gets me. So solving for n here, I can factor out n. That gives me n times sine theta minus mu cosine theta equal to that. So divide out by this thing that gets me n. So doing all that in my head, n is equal to mv squared over r divided by sine theta minus mu cosine theta. Okay, that's a version of n coming from 1 prime, so 1 double prime. Let me do the same thing using the second equation. So I have, once again, factoring out n, I have n times cosine theta plus mu sine theta. So I need to move mg over to the other side, divide by this thing. Once I've done all that, I get n is equal to mg divided by cosine theta plus mu sine theta. That's my 2 double prime. All right, now I can set these two equal to each other and solve for mu. All right, low algebra. Let me just do power through that and we'll be done. So doing that 1 double prime equal to 2 double prime, what you end up getting is mv squared over r divided by sine theta minus mu cosine theta is equal to mg divided by cosine theta plus mu sine theta. So masses cancel out. That's great. And I think what I'm going to do to get kind of expression where it's easy to solve for mu is I'm going to imagine multiplying this entire thing by product of basically these two things. So product of sine theta minus mu cosine theta times cosine theta plus mu sine theta. And the effect of that is on the left-hand side. This cancels out, leaving me with this. On the right-hand side, this cancels out, leaving me with this. So let me write down the version of the equation where all that has been done. And you get v squared over r times the thing on the right. So cosine theta plus mu sine theta is equal to g times the thing on the left, sine theta minus mu cosine theta. Now I need to collect like terms, by which I mean all the terms that contain mu. So let me collect them on the left-hand side and everything else on the right. So doing that gets me this. On the left-hand side, I have a mu times, and I'm going to write down the version where mu is already factored out. So I have sine theta, v squared over r. So v squared over r sine theta. That's what was originally on the left. And I have g times cosine theta that's moved to the left. So now the minus is going to become plus g cosine theta is equal to everything else gets moved to the right. So I have the thing that's already on the right, g times sine theta. Oh, wait. G stays there. Minus v squared over r cosine theta. V squared over r cosine theta. And so solving for mu, this is what I get. Mu is equal to, I have that complicated g sine theta minus v squared over r cosine theta divided by v squared over r sine theta plus g cosine theta. All right. It's not going to simplify anymore. The friction tends to complicate a bunch of expressions. I'm just going to leave it at there. Let me just plug in the numbers so that I can verify for you that the answer I got is correct answer. So let me actually copy this up where I have all the other numbers. And I have all my numbers here. In the calculator, let me just do it in two steps. Once for the numerator and once for the denominator. By the way, I can do this more quickly on a Wolfram Alpha, but let me just use calculator so that I'm not taking shortcuts with this one where I've already taken one shortcut. I don't need to take it with the remainder. So I have G, I'll just use 9.8. Let me not make this complicated. 9.8 times sine of theta. Theta is 21 degrees. Sine of theta minus, let me do parenthesis. The speed is 5.556 meters per second squared divided by the radius, 100. Times, and this particular calculator actually obeys order of operation. That's why I'm doing it this way. You should know how your calculator works. So yeah, so 20 cosine of 21. So that'll get me, when I press equals, that'll get me the numerator. So the numerator is 3.224, and the unit 2.224, and the unit technically is meter per second squared, although that's going to cancel out, so I don't care. All right, the denominator is going to be v squared over r, so 5.556 squared divided by 100 times 20 sine of 21 degrees, so 21 sine, that's the first term, plus 9.8 times cosine of 21. So 21 cosine is equal to 9.25, so 9.260. 9.260 meter per second squared, 3.224 divided by 9.260. By the way, if I were worried about rounding issues, then I could have used the memory storage function. But that's one of the reasons we want to fix the rounding issue, so that you can just keep 3 or 4 significant figures and you'll be fine. So 0.348. 0.348. Okay, let's plug that in. 0.348. All right. This is a good opportunity to at least illustrate how you approach kinematics problem solving. So this particular question has 2 parts built into it, and the question does kind of break it up into parts. So when you look at it, so it has a part where it's sliding up. So that's one part where you can kind of treat it as 1D kinematics. And it has a second part where it's now in the air undergoing projectile motion. So that would be projectile motion. So as you look at this multi-part question, you'll see that up through part A is 1D kinematics. Then B is kind of combination because you have to figure out the part in the air. And so we'll get started from the beginning here. So the question says a block slides frictionlessly towards a ramp at a speed v1. So that'll be the initial speed. The block slides onto the ramp without bumping or otherwise slowing down. So when it's on the ramp, moving up, at the very bottom, it's at speed of v1. The block slides up the ramp, then shoots into the air, landing on a plateau, and then comes to a stop as it lands. And the rough trajectory shown. It highlights the length given, and it tells you something about the angle, and I guess that's actually important not for this initial ramp up part, but it's going to be important for the projectile motion part. So angle theta with the floor while on the ramp, the block slows down with an acceleration of magnitude A. And this is an important information not to miss, since if you somehow miss that the question gave you the acceleration, then I've seen people waste the time doing the inclined plane question. And this question isn't calling for the at all. You are given the acceleration, and you just to use that acceleration to answer. So the question asks find the speed of v2 of the block at the end of the ramp as it shoots into the air. So with the kinematics questions, really the thing to do is what do you need to know? What do you need to know, and what quantities are known? So you have read through the question, so you know the known quantities. Known quantities are you are given the initial speed v1, you are given the acceleration, you are given the length or displacement. And I think that's more or less it. And you have the unknown. Usually there will be at least one unknown, which is the quantity you're trying to find, in this case V2. And you kind of run through the kinematics equations. This is where it's very useful if you have them memorized, because then it's quicker for you to go through the position expression, v naught t plus x naught, or the change of velocity. And the reason this would be useful is you can kind of rule them out quickly, that they don't give you the information you want. Mainly because all these expressions rely on time, and you don't have time information as one of the knowns. So if you have the kinematics equations memorized, it's quicker for you to run through the possibilities in your head. So here, really the key thing is that there is no time information here. So of the kinematics formulas, the one that's most useful here is the V squared formula. V final squared is V initial squared plus 2 times acceleration times the displacement. So the one thing you should remember is that these two, the direction matters. So when the acceleration and the displacement are in opposite directions, then there should be a relative negative sign between them. So, so this is the equation that I'm going to use since it doesn't require time information. So let me just write down a version of the equation with all the quantities from this particular problem. So my final velocity is the V2 that I'm looking for. V2 squared is equal to initial velocity is V1 squared plus 2 times, we are given the acceleration. And I guess this is where I have to be mindful that acceleration is going this way. So I'll just put in minus a times the displacement or the length of the ramp. Then, I guess it's more or less solved for already. Take square root of both sides and you get V2 is equal to square root of V1 squared minus 2AL. And that's it. It's I think most of the people in this class have reasonable familiarity with, especially 1D kinematics solving. It's quite a bit similar to a lot of math problems you have been doing before this class. So if there are no questions, let me move on. And so part B asks, find the total amount of time the block spends on ramp and then in air. The phrasing there would make me consider breaking up this problem into two parts, because there's the part of the time that the block spends on ramp. That'll be one part. Let me call that T1. And then in air, this is a second and separate part, because how I would handle this first part of 1D kinematics motion from the second part here, the 2D projectile motion, the approach there will be completely different. So I would treat this as basically two-part problem on its own. So I think most people in this class can find out T1. So for T1, you would basically go back to one of these kinematics formulas here. So I guess now that I know the final velocity, this is probably easier one. And I can, from this equation here, I can figure out my time t1 is equal to the difference in the velocities, v2 minus v1 divided by the acceleration given. And if you want, you can plug in the expression for v2. And so that's the one part of this part B. And for the second part, so this is where you have to remember the projectile problem solving strategy, the what you have been using when we are going through the projectile motion chapters. I guess that's chapter 4. So this is the typical setup where you have a projectile that's moving at some angle theta with some initial velocity v. In this particular case, it would be v2, and you are trying to solve, quote unquote, solve projectile motion. And by solve, I mean figure out all the relevant parameters. And that could be, in some scenarios, finding the range of the projectile motion. Another parameter that you might be interested in is how long, the duration of time it takes for the projectile to make that travel that trajectory. So that would be finding out this delta t would be another thing. So when we say solve a projectile motion, it kind of comes down to being able to analyze the whole setup and answer any questions. And what you have been doing for chapter 4 is you introduce coordinate axis. So you break up the motion into independent x and y components of the motion. So you start by saying this v2, this vector has the x component of velocity and the y component of velocity. And you write down two separate sets of kinematics equations, one that deals with the x component of motion and another that deals with the y component of motion. So the parts that deal with the x component, that they would look like the distance x is given by the initial x velocity times time. And because the acceleration in the x direction is 0, this is it. You get a very simple expression there. And for the y direction, the kinematics equations become a little bit more interesting. So the height, y is equal to minus 1/2 gt squared, because the acceleration in the y direction is minus g, plus initial y velocity times time, plus initial y height. And I guess there are a few more you can write down. For this question, I think it's a little bit easier to use the other equation, which is the final y velocity is equal to initial y velocity minus gt. So one of the first things you do in tackling a projectile motion question is you introduce the coordinate axis and handle the x and y component of the motion separately. They are connected by really one thing, that they occur at the same time. The time variable is the one thing that connects the x and y portion of the motion together. And I think in part C, I ask you for how far from the top of the ramp. Eventually, there's a question that asks you for the range r. And to answer that question, you do use the x component of motion by utilizing the time that you find from the y component, which you will do right now. So in order to find the t2, what we are doing right now is solving for time t here. And there's a few different ways how you can specify when the projectile lands. You can do it by saying, oh, that's when y is equal to 0, after having said y not is equal to 0. And if you have a little bit of physical intuition, you can do a little bit of a shortcut that avoids you having to deal with the quadratic equations. That would be to say, where the final y velocity is equal to minus initial y velocity. It's for a situation like this where it's a kind of a symmetry, it's a level ground where it lives and where it lands is the same, then you might have an intuitive feel that how fast it's going up is same as how fast it's coming down. If you have that intuition, great, you can use that little bit of a shortcut. And I'll use that shortcut right now. So that's where I'll use the second equation I wrote down and say that this is, so this becomes minus v2, that's the final velocity, is equal to plus v2 minus gt. So I can move this over to the left-hand side, move this over to the right-hand side, then I get gt is equal to 2v2, or time that the projectile spends in air is equal to 2v2 divided by g, or this is t2, and the total time that the projectile spends in air would be time is t1 plus t2, or the total time that it spends on ramp plus in air. And this is the information you can use to answer part C, where it asks about the range. So this question, it's trying to walk you through the steps that you should be going through to, once again, to solve the setup. And when we are vague like that, solving the setup, then what it means is you should be able to break it down. You should be able to analyze it in such a way that any questions on something someone asks, like someone asks you for the acceleration or the tension, you should be able to, in a relatively short set of steps. So, yeah. Okay, I guess we'll do all the parts here. It's so parts A and B, you did that in the lab, and C and D, it would be a fun thing to do. You didn't do it in the lab, so it'll especially be a fun thing to do. So, so it says draw free body diagrams. So I will draw free body diagrams. So, and really, what the steps here are having you walk through is the standard strategy. And so, you know, the question doesn't ask you to write down standard strategy. And frankly, I probably won't ask you any question where I ask you to spell out standard strategy, because it is one of the methods. You don't necessarily have to follow it. But hopefully this is in the back of your head as you're going through this question, that the very first step is drawing free body diagram. And that's what part A is asking. And in the second and third step, which will be very short for this question, you define coordinate axis, and mostly you pay attention to the direction of acceleration. That's what matters the most. Here, you're just looking at it accelerating either completely horizontally or completely vertically. So that makes your step number 2 a little bit easier. And step number 3, which is not existent here, is you break forces into components. But I guess this is more relevant for the next question. And once you are done through all these 3 steps, then you should have a free body diagram where you basically labeled everything, and all you need to do is copy over the information to write down Newton's second law equations. So with this in the back of your head, what you are going through is the very first step. Draw the free body diagrams for small mass m and the big mass m on the table. So free body diagrams. And so the thing to remember with the free body diagrams is you draw separate diagrams for each object in your setup. Here there's 2 objects, so we draw 2 separate diagrams. And sometimes people do this where people draw forces right on the pictures themselves, and I guess that's technically not wrong, but I prefer to draw free body diagrams separately this way. because it's meant to be a diagram of force only, and I don't want to be confused by these strings and other things that that's not force. So I have these two dots representing each of the object, and for each dot, I'm just going through what are the forces on that object. And each time I draw force, I verify with myself if I drew all the forces. So for this small hanging mass, well, I start out with the gravity. There's always going to be gravity pulling things down. Then I ask myself, did I draw all the forces? And I didn't, because there's this taut string that should be pulling things. So I need to draw tension. Then I ask, did I draw all the forces? And other than possibly friction, but it says ignore any frictional forces. So I'm done with the hanging mass. For the big mass on the table there, I start out with the gravity once again. So there's gravitational force pulling it down. Then as I ask myself, did I draw all the forces? What I'm really looking at is, does the direction of acceleration that seems to be implied by the forces I've drawn make sense? And here, I know this mass is accelerating horizontally. So the forces I have doesn't make sense. There must be a normal force that's balancing out the gravity. Then I keep asking myself, did I draw all the forces? And the one force I'm missing is the force coming from the tension here. So I need to draw a tension force. All right, so that seems to be all the forces. Just to be thorough, it says indicate any forces that are equal in magnitude. So I'm going to indicate this normal force and gravity are equal in magnitude. And I guess the thing I was trying to catch people is these two forces are not equal in magnitude. I was trying to draw them different in size, and it's because this mass should be accelerating downward, and this mass should be accelerating to the left. And for this mass to be accelerating downward, the tension should be less than weight. I think we went over that in the lab. All right, so those are the free body diagrams, and I indicated the direction of acceleration, so we are ready to move on. Part B says, find the acceleration of the two masses and the tension T in the string if the masses are free to move. So this is where having this standard strategy in the back of your head is useful, because then you will have seen you are done through steps 1 through 3, and what you are now doing is step number 4. And so the question doesn't ask you explicitly to write down Newton's second law equation, but that's what you need to write down in order to be able to solve for the acceleration and the tension. So writing that down, you should remember to write down this equation once for each object, and once for each direction. So here, for each object here, technically I might be writing down up to 2 equations. So potentially I could have been writing down 4 equations, but some of the directions here are very boring. So let's start out with the small mass m. So when we are looking at the net force on small mass m, let's do the vertical direction first. Then I have, so I'm going to let the direction of acceleration be my positive direction. So it's mg minus t is equal to mass times acceleration. And technically, I might need to write down the net force on small mass m in the x direction, but there are no forces in the x direction here. So it's going to be all just boring 0, 0, 0. So I'm just not going to bother with that and just move on to bigger mass m. So for the big mass m, even though nothing much happens in the vertical direction, I will write down something so that it's demonstrated. So so let's do the x direction first. So for the big mass m in the x direction, it's going to be a little bit unusual letting the leftward direction be positive, but I'll just do it that way. If you somehow made the rightward direction positive, then what you have to remember is you have to remember your acceleration is going in the negative direction. So rather than dealing with all that, I'm just going to say my leftward is positive. Then I can say tension is going in the positive direction, and that's equal to the big mass times the acceleration. And it's worth pausing for a bit and making sure that since I'm writing this in the equation, that these two tensions are indeed equal to each other in magnitude. And hopefully you can convince yourself of that. And that these two accelerations are indeed the same magnitude of acceleration. If they are not, then this is the step where you need to make sure you are using different letters so that you don't confuse them. Finally, for the y direction, net force for the big mass in the y direction, we have normal force minus mg, and that should equal 0 since it's not accelerating in that direction. So this is the third and last equation. I guess you would write it down if you are looking for the normal force somehow. But for our purposes, it doesn't add anything useful. Really, the first two equations give us everything we need. So we have equation 1 and 2 equations, and I always do this check, counting my equations and counting my unknowns and make sure those two match. So I have 2 equations and 2 unknowns, so I have a system of equations that I know should be solvable. The reason for this check is really to not waste any time. The whole reason for this standard strategy and this fourth step here is to systemize your problem solving so that you have a system of equations before you start actually trying to solve for a quantity. Because if you don't have at least as many equations as your unknowns, then you don't have enough information. What you really should be doing is reading the question more carefully and making sure you have all the information written down in a form of some kind of equation. So here, since I have that, then I can do it. I'll use a substitution. So this equation is already solved for tension. So I'll plug that into equation 1 to eliminate tension. Then I get mg minus big MA is equal to small ma. And now I should be able to solve for acceleration by collecting the like terms. That gives me mg is equal to ma plus big Ma. And the reason I collect like terms is so that I can factor out that a from the like terms. Now I can solve for a by dividing through by m plus big M. So acceleration is equal to mg divided by small m plus big M. So that's it. And this is what you did in the lab. This exam question just asks you for one more thing, tension. So let me do that. Tension is equal to big mass m times this acceleration. So big mass m times the rest of the acceleration. Hopefully I'm writing it relatively clearly, which m is capital M, which m is lowercase m. So, all right, that's it. That's my answer. So your lab ended it here, and that's pretty short exam question. So that's why in parts C and D we are asking for some additional things. Let me copy these over because I think this will be useful to have. Questions below relate to a change in the previous setup. Each change is independent of the other part. C, describe how acceleration and tension change or do not change if the positions of the two masses are swapped. And I want you to illustrate a kind of mathematical or problem-solving technique. So it's definitely possible for you to resolve the entire question after having literally changed the positions of the two masses. You can do that. Nothing stops you from doing that. But that involves a lot of extra work that you don't need to do. What you can do instead is something you can do with just the analytical results here. So what swapping the positions of the two masses really involves is swapping the labels, the small m and big M well, big M, swapping these two labels. Because when you imagine all the steps that I go through up here, if you just swap those two labels, small m and big M, that would be effectively the same as physically swapping the positions of the two masses, the big M and the small m. So, so what I'm actually going to do is just take the result here and just do this swap, algebraic swap of the labels, and say my acceleration with the swapped masses is, okay, so it's a big M times G divided by big M plus small m. And all right, that looks different from what I have there. This is definitely not equal to small mg over small m plus big M. The change that matters being this m here. So I hope it sort of makes sense that when it's the bigger mass hanging from the pulley, then they accelerate faster. Now, what's interesting is actually the tension. I don't know how many people will have expected this before going through the calculation, but when you write down the same thing for tension, for the tension in the string when they have been swapped, is, well, so it's a small m times big M G divided by big M plus small m. And when you think through it, this is equal to the original tension. When you look at it, it's, it just swaps where the two m's are, but since in multiplication, the order doesn't matter, nothing has changed. So these two expressions are in fact equal. And when you have those two masses swapped, then it doesn't, tension is still the same. It's sort of, I hope it's, well, for most people, it's unexpected how that works out. That so I guess how it works out is, so if you were holding the masses in place, then tension would have increased when the hanging mass thing was bigger. But because the acceleration is greater, that means for the mass that's hanging, the tension doesn't need to be as great as the weight of the thing hanging because it's now accelerating down faster. So anyways, so as far as the explain your answer goes, you could be explaining your reasoning process for doing this algebraic thing. And you can also, on the exam, you are on a clock, so I don't expect a whole long explanation. Because I'm pretty sure you can see that as I'm doing this bunch of explanation by saying things out loud, I'm actually going over time. Because during the actual exam, you should be doing these questions in about 1 every 20 minutes. So on the exam, be efficient with your time. Let's do question D. Instead of being frictionless, there's a coefficient of kinetic friction. It says find the acceleration of the two masses. Do I want to? Let me start from scratch. I will copy over one thing, which is what I wasn't asking you to do anyway. That's the standard strategy. Because the earlier part of the question kind of walked you through standard strategy. Part D, because you've done it once already, expect you to just do it on your own and not guide you through those steps again. But whether the question guides you through these steps or not, what you do doesn't change. You are still following the standard strategy. You're still doing the thing that makes sense for you to do when you're doing a force question. So, so with the new friction force there, what I would do is I would start out with the free body diagram. Even when the question doesn't ask me to, it still makes sense for me to start out with the free body diagram. So let me draw a free body diagram of the small mass m and the big mass m. So on the small mass, nothing changes. There's a weight and tension. On the big mass is where now there are changes. So there will be weight and normal force and tension. And with the friction, you have to think carefully in what direction the mass is moving. So when the mass is moving to left, then friction force is to the right. So you want to make sure you have it going in the correct direction. So friction force going to right. Oh, forgot to label the normal force. So, all right. So with the free body diagram drawn, the next thing I need to do is I need to define the coordinate axis. That's the same axis as before, the direction of acceleration. I'm going to label that as being positive, direction of acceleration. And I don't need to break any forces into components, thankfully. Now I can write down my net force equation. So net force on the small mass m is going to be weight, mg, minus tension is equal to mass times acceleration, same as before. And I won't bother with the x directional forces since there aren't any. Net force on the big block. Now here, I actually do have to deal with the y and the x direction. Main thing being that with the friction force, I'm going to want to know the normal force. So if for people who might have been ignoring normal force in part A earlier, this is where you do need to introduce normal force. So you have the force, let me say what in the y direction is the normal force minus the weight is equal to 0. And in the x direction, now it's a little bit more interesting. Instead of it being just a tension, it's a tension minus the friction force. That's equal to mass times acceleration. So here you have three equations. And what I'm hoping you will notice is you have more than three unknowns. You have tension, acceleration, normal force, and friction. And this is where you have to remember. So this is why I do the check. Because if I started solving this system of equation while I had only three equations and four unknowns, I would have gotten stuck and all that time would have been basically wasted time. That's why it's worthwhile for you to go through the check of do I have as many equations as unknowns, so that you can realize that you need more information. Here, the information that you would have eventually figured out is that the friction force is related to normal force through this relationship. Friction force is coefficient times the normal force. So, so this is my equation 4. And this allows me to get rid of one of the unknowns here. In fact, let me do that now. So this equation with the substitution of equation 4 becomes tension minus mu n is equal to ma. So let me call this equation 3a. Then I guess I should be systematic. So now I have 1, 2, 3 equations with 3 unknowns. So the way you want to be systematic, deliberate, organized in working through a system of equations is you want to eliminate one unknown at a time. And as you're eliminating them, you want to do it kind of thoroughly. And so here, the decision I'm going to make now is to decide to eliminate normal force from my system of equations. The normal force occurs in 2 places, so I decide which equation I'm going to use to solve for it, and use that as tool to eliminate it everywhere else. This equation is a little bit simpler, so I'm going to use this to choose to solve for normal force there. So normal force is mg. This is one of the simpler scenarios. now I can use this to eliminate normal force everywhere. Here I have only one equation where I need to eliminate, but if it were somehow in this other equation, then I would do it there too. So using that, this becomes now T minus mu mg is equal to ma. So so this is my one equation, and I have one more, well, one equation that I haven't used so far. So considering this, and let me just copy that down here, mg minus t is equal to ma. Here now I have two equations and two unknowns, similar to part A. So I'm going to do the same thing I did in part A, with a small difference being neither of these are solved for tension, so I have to solve one of them for tension. I think before it was this equation that was already solved for tension, but now I have to move the other term over so that I have mass times acceleration plus mu mg. I can plug that into the other remaining equation to get rid of tension and have only acceleration to solve for. So it's mg minus big MA, again minus mu mg is equal to small m times acceleration, collect the like terms, and then solve for acceleration. When you go through all that algebra, I hope I'm not skipping any step that'll confuse someone. You end up with the acceleration is equal to mg minus mu mg. I'm writing down these two terms here, and I'm dividing by what's going to be on the right-hand side after I factor out a. So small m plus big M. So this is the new acceleration. And I think once you solve for it, it's kind of intuitive that it's very similar to the previous acceleration you had, except for the quote-unquote net force is the weight on the small mass minus the friction on the big mass. But it's good to make sense of your answer and make sure it makes intuitive sense as well as being correct this algebraically. So so this is the type of force problem solving that I'm hoping everyone will get very used to, and that there's a kind of infinite variations you can do here. And once you master application of this standard strategy, then all those different variations, what they'll do is you might have to spend more time, but hopefully you will never be stuck trying to solve something. So question 21, I gave this, I guess last time in spring 2017, pull with the friction. This is basically my one question that combines a lot of aspects of Newton's law problem solving in the context of having to deal with only one object. And having to deal with only one object actually makes things pretty nice. The biggest of which is that you don't have to worry about Newton's third law. When you have multi-block process, a lot of times people forget about Newton's third law and make mistakes there. So this being a one object problem kind of bypasses all of that issue. So with that, let me kind of just start right away. It says, so that's the description. It's being on the horizontal plane, it's being pulled, and and it's giving me the kinetic friction coefficient between the block and the plane. I think I put that in so that this will also be a friction question. Good. So, all right, let me start out with the free body diagram. So the free body diagram of the block, so here's my representation of the block, single dot. I try to make it as simple as possible because a free body diagram is a problem solving tool. You really don't want to complicate it. You want it as simple as possible. And for this, dot is as simple as possible. So I need to draw forces, starting with the forces that I identify as being necessary. And one of them, kind of obvious, oh, this might be blocked by my video, is tension. So I need to draw tension at an angle, T. And once I draw that, then I realize, oh, but that's not the direction that the block is accelerating. Block is accelerating that way. So I must have something that's balancing that upward component. So I must have the downward force of mg. Now, you could easily end there, but there's this odd phrase from the question. It says, assuming that the block remains in contact with the plane, then you should wonder what that means. And what the eventual answer is that if it's remaining in contact, that means that there is normal force. That is not zero. That is positive. So I need to draw normal force. Even though I guess somehow the situation could be set up where normal force almost goes to zero, but that kind of depends on what the value of tension is. And I don't know that normal force is zero yet, so I need to write this down. And writing this down reminds me that the question talks about the friction force. So I need to draw friction force. So if the block is accelerating to the right, I must have friction force to the left. That's going to be canceling out some portion of the horizontal component of tension force. Yeah. So that's the free body diagram. And I think you can stop here for the free body diagram. And let me go through the remainder of the question, part B. I can bring up some of the considerations in that part B. It says, find the acceleration of the block, follow the standard strategy, and give your answer in terms of all that. So I've already done the first step in standard strategy, actually. I drew a free body diagram. So that's my step number 1. So I need to step number 2, which is defining my coordinate axis. And my acceleration is horizontal. So that seems like a reasonable coordinate axis. That's step number 2. And I need to step number 3, decomposing forces into components. And it looks like I have only one force that needs to be decomposed into x and y component. And I think I am actually given the angle theta up there. Yeah. So let me write down theta so that I can kind of figure out that the x component is t cosine theta and the y component is t sine theta. All right, that's step number 4. Finally, step number 4, I need to write down the Newton's second law equations. I have one object, 2 dimensions, so I need 2 equations. So my Newton's second law equations are net force in the x direction. So that would be the x component of tension, t cosine theta, minus the friction force is equal to mass times acceleration. And I have the net force in the y direction is equal to normal force plus I have the y component of tension force, Ty or T sine theta, minus mg. And since it's not accelerating in the vertical direction, that's equal to 0. All right, so I have 2 equations. And let me count the unknowns. 1, 2 equations. And then my unknowns are, I know tension, I'm given tension, I think. I don't know friction force, I'm not told that. I'm asked to find the acceleration, so I don't know that. And I don't know normal force. 3 equations, so that means I need one more equation. And this is where I hope you kind of think through what forces you are given and how you can get information about that particular force. Because one thing that I haven't made use of is that this is a friction force. And there's actually a formula for kinetic friction force. So let me write that down. the formula for kinetic friction force is the coefficient of friction times normal force. So looking at this here, okay, this last equation didn't introduce anything we didn't know. We were actually told what the numerical value of, oh wait, we aren't. Okay, so I need to keep that. So yeah, so I now have the third equation and no new unknowns. So 3 equations, 3 unknowns ought to be solvable. Let me solve that. So one thing I do know is that I want to get the acceleration of the block at the end, which means what I make sure not to do is I solve for acceleration right now. Instead, what I need to be doing is solving for normal force and frictional force. So, all right, let me solve equation 3 for normal force. Then I have normal force is equal to friction force minus mu. So that's 3 prime. So let me take this take this expression for n that I solved and plug it into equation 2 to get this expression. So n, let me write it down, the friction force over mu plus t sine theta minus mg is equal to 0. I'm trying to solve for acceleration. I don't know the friction force. So what I should do is I should solve this for friction force. Let me just do this in my head. That's going to be mu times mg minus t sine theta. Plug that into the equation 1. Let me call this equation 2 prime. So from equation 1 and 2 prime, this is what we end up getting. T cosine theta minus that complicated expression for friction force, mu mg minus t sine theta is equal to mass times acceleration. So all I need to do is to solve for acceleration. I can, as I do that, I can simplify this a little bit, so I will. I'm just gonna kind of collect like terms, but you don't have to. I'm doing it for the fun of it. So let me solve this for acceleration here. One term I'm going to pull out is all the terms dealing with the tension. So I'm going to have tension over m, and I have things inside the parenthesis, cosine theta, that's this one. And I need to be careful with this one here. It's minus mu times minus sine theta. So it's plus mu sine theta. And what this really means is this is actually vertical component of tension that's helping you reduce the friction force by reducing this normal force here, because this amount of tension force helps you reduce the normal force needed. All right, I did that. I have one more term here. That's going to be minus mu m, m cancels out, minus mu g. And what this is it's the friction. It's whenever you have larger friction, that's gonna be slowing down your acceleration for a particular amount of tension and at a particular angle that you're going to apply. So yeah, that's the answer here. Acceleration is that. And once you have this analytical expression, that becomes a tool to answer other questions.
So what C is getting at is maximizing this acceleration with respect to theta. So we'll do that. Let me copy over this expression so that I have it to use. So this is the expression for theta, expression for acceleration as a function of theta. So let me just make that note clear that we are looking at this as acceleration as a function of theta. So the question says, at what angle should you pull so that the acceleration is the greatest? And it's the phrases like greatest or smallest that I hope that reminds you of the optimization algorithm that you learned in calculus. It goes briefly, it goes like this. If we have some function as a function of x, and you want to find where this is extreme, maximum or minimum, then what you do is you take the derivative of the function with respect to the parameter you are looking at, and you set that derivative equal to 0. And there's a value of x where this happens. And once you find that value of x, if you're looking for maximum or minimum value, you'll have to plug that back in to find the value of function. Or if they're just asking you at what parameter is it maximized, then you just finding the value of x that does this. That's your answer. So we're going to do exactly that here, except our function is a and our x is theta. So let me just take the derivative of this with respect to theta. And this is technically a partial derivative in that of all my parameters, variables, I'm only treating theta as being something that could potentially change. So I'm going to treat tension, mass, mu, g as constant, which might be, but tension could be a variable tension. But they did say fix the magnitude of tension t. So let me take the derivative. So this term goes away. It's constant with respect to theta. And so I'm looking at these two terms. Let me just write down the coefficient first, t over n. Derivative cosine of theta, and remembering my derivative formulas, it's minus sine theta plus, I have coefficient again, mu, times the derivative of sine theta is cosine theta. And as part of that optimization process, I want to set this equal to 0. And because we are setting this equal to 0, this makes sum of algebra easier. We can just cancel this out. Imagine multiplying both sides by m over t. That cancels that out. So I just have to worry about this adding up to 0. Okay, let me just write it down. Sine theta minus sine theta plus mu cosine theta is equal to 0. Which means just going to do the algebra in my head to get tangent theta is equal to mu. So I move the sine over, divide by cosine, that's tangent theta, that's equal to mu that was left over. um, uh, yeah, hopefully that's okay. If that's confusing you, pause the video, do the algebra by hand on paper, and make sure you agree. Now, were we given the value of mu? Let me check. We were not given a value of mu. So I think I'm going to make an assumption that the angle theta that will maximize acceleration, that this will be an acute angle. And I think that makes a physical sense. If you're somehow pulling this at, at an obtuse angle, then you are accelerating the wrong way. So I think it makes sense. It's going to be an acute angle. Under that assumption, that's well justified, you can put this through an arctangent function and say theta is equal to arctangent of mu. And this kind of reasoning is something that you have to go through every time you use inverse trig function. Because inverse trig functions are some of the least well-behaved functions, and you want to make sure that the parameter that you're looking for is well constrained, so that you are working within the well-behaved portion of the inverse trig function, or you are just, making corrections by hand as needed. So that's C, relatively easy once you have answer to B. Now D, it's so my recommendation is you do it from scratch. Now it is possible that you could reuse some of what you've done for A and B, but I think the headache for that is not worth the amount of time we would save. So we'll just redo all of them, and just do it quickly so that I have time for other questions. So let me. So I'm following the standard strategy. Step number 1, I'm drawing free body diagram. So free body diagram for this setup is going to be, I'm always going to have gravity, mg. And so I guess I'll always have normal force. And oh, and I have applied the force of F that's going in this direction this time. So it'll be drawn something like this way. Let me diagram the angle so that I have a good sense of that. I think that's correct. And finally, with all these forces, because they tell us something about friction, we'll have to make sure not ignore friction. I know I love to ignore friction, but whenever a question tells me something about friction, I can't ignore it anymore. So the role of friction always is to minimize the sliding between surfaces. Here, with all these forces, without friction, the block will tend to slide to left. So what friction will have to do is act to right, so that it prevents or reduces the sliding. So I'll have to have friction pointed this way along the surface, perpendicular to the normal force. So, all right, that's my step number one. Don't think I forgot anything. Now, step number two, I have to define my axis. So, in the event where friction is not large enough, this will be sliding to the left. So that's going to be my positive x direction, and my y direction will be this way. That makes sense. So that's my step number two, define the coordinate axis. Step number three, I need to break down my forces into components. So the only force that needs that is my applied force. Let me draw the component y and x, and this is theta. So my y component is going to be f sine theta. It's the opposite side, and this is going to be f cosine theta. It's the adjacent side. All right, I think I'm done there. So finally, I'm ready for step number four, which is the writing down of Newton's second law equations. And hopefully, once I've done that, I can see what else do I need to completely solve this question. So I have one object, two directions, dimensions. I'm gonna need two equations. So I need the equation for x direction and for the y direction. I often like to ignore the y direction, but whenever you have friction, you can't really because you need the normal force. So, okay, so x direction. I have the x component of applied force, f cosine theta. And at this stage, I like to put my directions into equation. So when I see my friction force is going in the negative x direction, I like to say minus f. So that I'm expecting f to be positive. So if f is ever negative, that tells me something. So that's going to be equal to mass times acceleration. The y direction forces, I have three forces. I have to be careful. Normal force, y component of the applied force, and gravity. So normal force in the positive direction minus the y component of applied force, and then minus mg is equal to 0. That's really the role of the normal force. It prevents acceleration or moving or in that direction. It just keeps the thing on the surface. Okay, so I have two equations, equations 1 and 2. So it's time to count my unknowns so that I will I will know if I need to go looking for more equations. If I have only two unknowns, then two equations, that's great. I should be able to solve for them. If I have more than two, then let's think more. But this is the end of the standard strategy. Note that it doesn't actually solve the problem. It just leaves you in a place where now you can actually start solving the question. So counting my unknowns, I don't think I know the applied force. It's saying you find a certain angle, it does not budge regardless how much force you push. So F could be infinity, but I don't know F. I think that's what it comes down to. I don't know friction, and acceleration. I think I know because it's not going to budge. So I can say my acceleration is 0. That's useful, I think. Let's keep going. Okay, I don't know normal force. So already I have three unknowns and two equations. And this is where, as you have stared, hopefully you realize, oh, we were given the information about friction force that we didn't use. So let's write it down. Um, so, so friction force, if it's a static friction force, then what we can say is it's less than or equal to mu times the static friction coefficient times the normal force. Now, let's say we are looking for an extreme case. This theta max being the threshold where something begins to happen or begins to not happen. So under that condition, we can say we are looking for a situation where my friction force is equal to that maximum value. So this is my third equation. So I have three equations. The three unknowns, I think we should be able to solve it. So let me do it this way. I think, so I've done this type of question many times. You do need to be deliberate when you are solving for system of equations. One that I think is helpful is if you have an equation, um, actually, I guess here technically you don't know F. So no, a lot of times this is the equation with only one unknown, the normal force. But regardless, I think it's nice to just solve this for normal force, plug it in here, and we can just eliminate normal force that way. And the rest of the question, we don't have to worry about normal force. So let me do that. I'm going to solve this for normal force. N is equal to mg plus f sine theta, and I can plug it in here. It's the only equation with the normal force in it. Then I get friction force is equal to mu times those. So mg plus mu times f sine theta. And I can plug that in there to eliminate force F. Oh, and I think I see a trouble and a solution. Let me first write down that one final combined equation and talk about both. So this comes from equation one with all the substitutions. It's going to be f cosine theta minus these two. So minus mu mg minus mu f sine theta is equal to, well, not mass times acceleration, I guess, but 0. Now the trouble that I was identifying was I forgot to count an unknown theta. I don't know that unknown theta because we are looking for angle theta, so it's an unknown. So it might look like we have one equation and two unknowns, and that is right. And this is where I think it helps to think a little bit through, because what the question is saying is that the block does not budge regardless of how much force you push the block with. So I'm just staring at this for a bit. Let me just play with it for a bit. I'm gonna, hey, what does it look like when I solve this for f for the time being? Imagining I know theta, even though I don't. So if I do that, I'm gonna collect the like terms with the f. So I have f times, I'm factoring out f cosine theta, and I have minus mu sine theta, and then I'm gonna move this over. So I have plus mu mg. Okay, let me just finish solving for mu. I mean, sorry, f, and I think it'll give us something to think through. So solving this for f, I have applied the force f that I would need to apply to be right at the limit of where the block is about to slide. That's what the meaning of this f is. That is equal to mu mg over cosine theta minus mu sine theta. And I hope as you stare at this expression for a bit, you get an inspiration, um, or one of those poorly motivated solution steps where I don't know. There's no like systematic way to get at that. So I'm looking at this expression, thinking I'm looking for a situation where it doesn't matter how much force Fi apply, F is basically going to infinity. And as you're thinking that, I hope you notice this, that we are dividing by a quantity that could go to 0. So if this quantity is going to 0, that's going to make the requirement on this f to go to infinity. So just going over here and just setting up, okay, let's see if we can make this denominator go to 0. Cosine of theta minus mu sine theta equal to 0. Hey, I think I can. Move that over, So doing the algebra, just gonna do that in my head. You get tangent theta is equal to 1 over mu. If necessary, I skipped like 3 or 4 steps of algebra, so if necessary, pause the video and just work through it carefully, step by step. And and mu, let's see if we are given the value of mu. Um, Even if we weren't. And actually, the tangent theta being the kind of function it is, mu can be actually anything. Mu can be anything from something bigger than zero to something approaching infinity. We'll still get a value of theta that's an acute angle less than 90 degrees. So we can say, oh, so theta, the theta angle at which this wonderful thing happens, where the denominator goes to zero and up required force F approaches infinity, that angle theta is given by arctangent of 1 over mu. And that's the answer. And there are other follow-up questions people could ask, like, so what happens if your angle is greater than that? And at some point, you're going to have to question some of the assumptions that went into problem solving. This is actually technical inequality, all that stuff. But yeah, so this is the kind of question where getting to this far, getting up to either this step here or this step here, that's what standard strategy is for. It'll get you to a place where you can start thinking about the setup and start working towards the concrete solution. And for easy questions, basically all that's left to do is finish the algebra. For harder questions like this one, you have to think more. You have to be more creative in what kind of things you are looking for. So that's what this is.